Today's lecture is a continuation of our previous lecture, which was chapter 8, Compaction and Settlement. We took a very quick introduction about the settlement. Mainly, of course, we started with the settlement. We said that the settlement may have three parts. It is a consolidation settlement. It is we first have something called ST, which is the total settlement. Total settlement is the sum of three things. SC is the primary consolidation settlement. S, which is the secondary consolidation settlement. SE is the elastic settlement. So if I was going to put, I would take elastic settlement at the beginning because it is the immediate part. Elastic settlement is the first part, followed by the primary consolidation settlement. These are the major parts. Then they may be something called secondary consolidation settlement, or sometimes they call it creep, which is consolidation settlement, but it takes a very, very long time, and sometimes it is creep. It has nothing to do with consolidation, and it is only because of the change in the shape of the particles itself. In all types of consolidation, we are speaking about the voids. The voids are decreasing and expelling water, or decreasing and expelling air. Decreasing and expelling water, it's consolidation. Decreasing and expelling air, it is immediate settlement. But there is another type of settlement which is called secondary consolidation or creep, and sometimes this creep happens for sand. It is because of the change of the shape of the particles itself. Maybe particles would turn a little bit to the right, to the left, to fit better in a space. So there will be a reduction in the total volume of the sample, and this reduction, it takes a very, it may take a very long time, and the percentage of it of the total settlement is not big. So usually we can ignore this portion, which is the secondary consolidation settlement. In many cases we find that it is not calculated. We only take the elastic settlement and the consolidation settlement, and that's all. But if I want to make a more elaborate calculation, then I should take the secondary consolidation settlement or the creep into consideration, and so on. This is the creep settlement, and we've seen the different types of settlement and how it happened, and so on. So it was all descriptive. In this lecture, we are going to start to know how to calculate the elastic settlement that would happen in the soil. If I have a case of footing resting on a limited soil layer thickness, if I have a thickness of a layer which is H, and I want to calculate the settlement of this layer, this is very easy because I have, this is, we can call it Hooke's law, or the elastic deformation or the elastic behavior of any material. It is something related to E, which is equal to the stress divided by the strain, and from this equation we reach this shape of the equation, which is SE, which is the elastic settlement, which is equal to delta H, or the change in the height of the layer, of the compressible layer. It will be equal to delta sigma, which is the increased stress. Because why do we call it increased stress? Because soil already has stresses inside due to own weight. Due to own weight of soil, you have stresses inside the soil. So it is not zero inside the soil. There is stress. But if I add additional load on top of the soil, then I will have something called delta sigma. If I tell you calculate sigma inside the soil, then it is the stress due to own weight. This is the sigma inside the soil. But if I tell you calculate delta sigma, it means that the additional stress that you add to this soil, so this is delta sigma, multiplied by H, which is the thickness of the compressible layer, divided by E, which is Young's modulus of the soil. So this is in case of if I have one layer with specific thickness. Suppose I have multi-layers. I don't have just one layer. This is 1, 2, 3, 4, 5 till n, layer number n. In this case, I will calculate the stress, the settlement of each layer alone. I will take this layer, calculate delta sigma at the middle of this layer, which is the stress at what is the value of the additional stress that will reach this layer. I will take this delta sigma, and I know H, which is the thickness of this layer, and divided by E, and so on to get the change that will happen, which is delta H that will happen to this layer. Then I calculate the same for the next and the next and the next, and then at the end add all of them together to get the total settlement that is expected to happen. So as you see, to calculate the settlement of these layers, I need some parameters. I need to know what is the value of the E of the soil, Young's modulus. I need to know some soil parameters. So usually I have tables just to give you an indication. This is the value of ES, which is Young's modulus of soil, in case of different types of soil. This is just to know an imaginary numbers. For soft clay, this is the value. For hard clay, this is the value. For loose sand, this is the value. For dense sand, this is the value. This will give you an indication of what? For clay, starting from soft clay to hard clay, these are the values. The maximum value for hard clay, it is 6,000 to 14,000. For loose sand, it starts with 10,000 to 28,000. So, always clay is less in strength than sand. But of course, you may have hard clay that is reaching very high, maybe not hard clay, maybe very hard clay. So you will find numbers that are more than that. There is also another parameter. It's not very important in our analysis, but you need to know it, which is Poisson's ratio. Poisson's ratio is the effect of the vertical load on the horizontal direction, or the vertical stress on what will happen in the horizontal direction. It is not very important in many analyses, and as you see here, you have values ranging from 1800, which is 1800, till you reach 70,000. The range is very big. But here, if you look at these values, you find that from 0.2, 0.4, 0.25, 0.4, 0.3, 0.45, 0.2, and so on. So, if I take a value of 0.3, it will fit in all of the soils. So the sensitivity of the parameter is not very high. If I don't know Poisson's ratio for a certain sample, I can easily assume it without big loss in accuracy. But if I don't know what is ES, I will be using, suppose you assume 70,000 for soft clay. It's a catastrophe. But here, if you use these values, take the average value, it will be fitting in most of the types of the soil. Then look at the equation. What are there in the equation? SE or delta H, this is what I need to know. What is the settlement? E, we said that it is Young's modulus. This is how I can get it. I can get it from tests in the lab, tests in the field, or from published data. So this is E. Then what is remaining? H is the thickness of the layer. What is remaining is delta sigma. This is very important. What is the additional stress that I'm inducing on my soil? Then I need to calculate what are these additional stresses that I'm inducing on the soil. You remember that in chapter 4, total and effective stress, we took many things in case of having a point load, a line load, a uniform load. If you remember, there was something called Newmark chart, and we used this Newmark chart to calculate additional stress inside the soil. So if you refer to this lecture, total and effective stresses, you will find that how we were calculating additional stresses inside the soil due to external loads, whether these external loads are point loads, line loads, or loaded areas. This is what we are going to do here. We are going to calculate these additional stresses, just remembering what we took before. For a loaded area, whether square or rectangle, this is how we can calculate it. You will see it now. We said that we have an approximate method, which is the load distribution. Instead of taking the effect of the stress at a point, we take the effect of the stress at a level, at a certain depth below the soil. And this was an approximate method, and we had Newmark chart. Let's remember the three very quickly, but of course, if you need details, you have to return back to your lecture. This was the shape of the additional stress in case of a loaded area. This is the chart that I'm going to use. This is the loaded area. I need to calculate the stress at this point at a depth Z at the corner of a loaded area. I can use this chart. I have here two factors, I4 and N. I calculate I4 and N. Let's see what is I4 and let's see what is N. We have N and we have M. N and M. These are shape factors. M is Z, X divided by Z. N is Y divided by Z. So I have a dimension. This dimension is, it has a loaded area that have dimensions, and I refer the dimensions to the depth Z. I will calculate M and N, use M here, N here, go to the curve of N, cut it in a point, go horizontally, get I4, apply it in the equation to get the delta Z, which is the stress at a point at the corner of a loaded area at a depth Z. So this is the first method. The second method, we said that I have, say, a footing, and I want to calculate the stress at this point. To calculate the stress, it's not only at a point, it's a layer, it's a level. If I want to calculate the stress here, then I will take the same load, divide it by the new area at the bottom, and this new area, how I can calculate it, I will just use a sloping line here with an angle 2 to 1 to reach this bottom. So this will be the new dimensions of the footing. Instead of having a footing of dimension B by L, it will be B plus Z multiplied by L plus Z. So this is the new area. I will divide the load P by this new area to calculate, to get the additional stress at this level. Of course, this is not very accurate because it assumes that the stress at this point is the same as this point, as this, and so on. And if we check here, we will find that horizontally, no, there will be a difference in the stress according to the location of your point below the loaded area. So it is an approximate method, but it is very good in calculating the stresses due to rafts and footings and so on. The other thing is Newmark chart. We said that Newmark chart is a very powerful means to calculate this. Newmark presented this drawing with this scale at the bottom. This scale, the distance between A and B should be equal to the depth where I need to calculate the stress below the footing. So I use this as a scale, draw my footing with this same scale. If I want to calculate the depth at the stress at a depth of 5 meters below the footing, so it means that from here to there, this is 5 meters, and I will calculate at this location. I will just adjust this AB to be equal to the 5 meters depth below the soil. So if I have a rectangular footing 5 by 5, so I should draw on a piece of paper, a separate piece of paper, just a square with this distance to be the side of the footing, because I need it to be also 5 meters. And I will just take this square, put it on top of this Newmark chart at the location where I need to calculate the stress. Suppose you want to calculate the stress at the center of the footing. So you will put the center of the footing at this point and put your footing here, and then count all the small squares inside. Calculate the number, this number multiplied by 0.05 multiplied by Q, which is the stress of the footing. You will get the additional stress at this location. So these are the three ways to calculate the additional stress. Here is an example, a plan of a uniformly loaded rectangular area. So it is a rectangular area. Determine the settlement of point A in case of thickness of soil layer is 8 meters, and so he gave me the thickness of the layer, and he gave me the E of the soil, and he wants to calculate the settlement at a point A at this location. The settlement is I will use Newmark chart, because in Newmark chart I can calculate the stress at this the additional stress at this point, and then I can take this additional stress, multiply it by the equation for the settlement to get whatever I need. We said that all of these three methods are just to give us a way to calculate this. If I can calculate this and I know H and I know E, then I will get the settlement. That's all. So I will use Newmark chart to calculate this. But I can use any method, by the way. I can use any of the previous methods, depending on which one that I can apply. But here, if we take this one, you will find that here, this one, you will find that I need a point at the corner, exactly at the corner of a loaded area. But here, the point I need is not at the corner of a loaded area. So I may use something called superposition. Add two cases together to get the case that you need. What are these two cases? Imagine that I will extend the load to this, to cover this 1 meter. In this case, I can calculate the stress at the corner here, because it will be a corner of a loaded area. And I can calculate this small area alone. I can take it alone here. So if I calculate my problem twice, one from this point till point A, so it will be 3 meter plus 1, it is 4 meter. And another case, it's just 1 meter from point A dash. And I use the difference between this case and this case. So if I subtract this loaded area from this loaded area, I can get this one. So this is exactly what I need. So I will solve the problem twice. One for this and one for this, and then subtract the values I got from each other to get this value. And so take this value, substitute in the equation of settlement. This is the equation of settlement, and you will get the settlement, and it will be 3 millimeter. So I use Newmark chart first to calculate the effect of the delta sigma, which is the additional stress. I calculated by superposition of two cases, one with positive and one with negative, add them together, get the number you need, substitute in the original equation of the settlement to get the settlement at this point. So now we calculated the immediate settlement. It means that if I have a footing and I tell you the stress, I tell you what is the dimension of the footing and what is the load of the footing. So you can calculate the stress beneath the footing. If I tell you calculate the settlement 10 meters below this footing at the corner, you will apply it, get the stress, and get the stress at the point that you need to calculate, apply the equation for settlement, and you will get whatever you need. So this is a way for solving this. This is in the horizontal direction. I mean studying the load on the top. Now, if we go to the bottom, here I was assuming that the soil is one layer. Suppose the soil is not one layer, it is multi-layers. In this case, the problem will be different. Why it will be different? Because suppose you have this problem, you have a gravel layer of 5 meters and a clay layer of 8 meters. So in this case, I will have to check the settlement or to calculate, it depends on what the example needs. If the example needs to calculate the settlement, then we have to calculate the settlement of all of this. What does it say? A soil deposit consists of 5 meters of gravel overlaying, so this is 5 meters, overlaying 8 meters of clay, so this is 8 meters of clay. Initially, the water table is 2 meters below the surface of the ground. So here the layer of the gravel is split into 2 layers. One with water and one below water and one above water. Of course, if I have this is the water table, it means that all of the clay is below water because it is far below. Knowing the soil deformation modulus of what is the soil deformation modulus? Young's modulus. It's E of the soil of gravel and the clay R. So he gave me the E of the gravel and the E of the clay respectively. Calculate the soil deformation due to rise of water table. This is very tricky question. Why tricky? Because water table was here. When water table rises from here to there, it means that there will be a change in the loads. Why? Because now this load was affecting all of this, and this load was a total load. But when water goes up, it means that the load will change. It may change by positive, it may change by negative. This is what we are going to see. So what we are going to do in this problem is the following. So I will just calculate effective stress at the middle of each layer. I have 3 layers, mainly 3 layers. They were initially 2 layers, clay and gravel, but the gravel is subdivided into 2 layers, one without water and one submerged with water. This is in the first case. But in the second case, water level changed from here to be there, so all of here is now the same. It is all saturated with or submerged with water. So we will just calculate the effective stress at the middle of this 2 meters, and then at the middle of this remaining 3 meters, and then at the middle of this 8 meters, which is at this point. So I will calculate it for the first case, and then I will calculate it for the second case. For the first case, I had these 3 numbers. For the second case, the numbers were reduced from 18 to 8, and from 54 to 34, and so on, from 112 to 92. Then I can calculate now the effective stress at mid of each layer as described. So thickness, now we calculated this in the previous. It means that we will have soil heave and not settlement, because the stresses were reduced. I cannot say that due to this the soil will be compacted. No, it will not be compacted. There will be a heave. What is the value of this deformation? I will apply in the equation for the this is the equation for settlement. I will just go to the equation itself. Where is the equation? This is the equation. Delta H, which is the settlement, is equal to the change in the stress that was supposed to be positive multiplied by H over E. But here, if I come to calculate delta sigma, I find that delta sigma will be a negative value. It means that it is a heave. So I will just go to this equation again, substitute in the equation, and get all of these values. We will find that the change in the stress, 8 minus 18, here 34 minus 54, and so on. So it is always increase. The stress is there is a reduction in the stress. From the values that we have calculated, this is the value. Of course, here they are given in positive number, because we said that it is heave, it is not settlement, so it is moving up. Look at this value, look at this value, and look at this value. Here 0.003, here 0.009, here the 0.08. So this number is very high compared to the others. Why this number is very high? Because this is clay. So clay is expected to settle or to heave more than other material. So this is something that we need to be to understand when we come to calculate different types of material. Suppose I have rock and I have sand. If you want to calculate the effect on the sand, but ignore the effect of rock and consider the rock to be that it will not settle at all. Why? Because the amount of settlement that you will get in the rock, if you have settlement in the sand, say 5 centimeters, in the clay it will be 0.005 centimeters. It is nothing. So you can ignore it easily. We'll stop at this part, and we'll continue the next part now also.